In August of 1817, in a small town in the Ganges Delta called Jessore, in what is now Bangladesh, a woman woke up thirsty. By sundown, she could not stand. By the next morning, she was dead. Her body so dehydrated that, in the words of the British East India Company surgeon who examined her, she resembled a corpse weeks old. She was one of the first. Within 7 years, that same illness, moving along trade routes, military supply lines, and pilgrimage roads, had killed millions of people on 3 continents. It would become known as the first cholera pandemic. And it would reshape medicine, public health, empire, and the modern city itself. But the spark that lit that fuse was not in Bengal at all. It was a mountain 2,000 miles away that had blown itself apart 2 years earlier. What you are about to hear is a chain of evidence that scientists have only recently been able to assemble. A chain that runs from a single Indonesian island, through the Earth's stratosphere, into the chemistry of the Bay of Bengal, and out through the bloodstream of the 19th century. It is the story of how a volcano in Indonesia wrote the world's first pandemic. Mount Tambora sits on the Indonesian island of Sumbawa. Today, it is a 6-mile wide caldera ringed by villages that have grown back over 2 centuries of buried ground. In April of 1815, it was a 14,000-foot stratovolcano. Then, on the evening of April 10th, it produced what remains the most powerful volcanic eruption in recorded human history. According to a 2016 review published in the journal Wiley Interdisciplinary Reviews Climate Change, the eruption injected roughly 60 megatons of sulfur dioxide into the stratosphere. That is approximately 6 times the volume released by Mount Pinatubo in 1991, and Pinatubo, on its own, was enough to measurably cool the planet for 2 years. The detonation from Tambora was heard 1,600 miles away, in what is now Thailand. Ash fell on ships at sea. The mountain itself lost more than 4,000 feet of elevation, collapsing inward to form the caldera you can see from space today. The immediate death toll on Sumbawa and the surrounding islands is estimated at 100,000 people. In 2004, an archaeological team from the University of Rhode Island, led by volcanologist Haraldur Sigurdsson, excavated a village that had been buried under the ash for nearly 2 centuries. Inside one home, they found the remains of a woman. She was holding a knife. She had been instantly turned to charcoal by temperatures higher than those that buried Pompeii. That was the local catastrophe. It was terrible, and it was brief. The global catastrophe, the one that killed for the next 8 years, happened high overhead, in the stratosphere, and it began with chemistry. When sulfur dioxide reaches the stratosphere, it converts into sulfate aerosol. These are microscopic droplets that reflect sunlight back into space before it ever reaches the ground. Tambora's aerosol veil cooled the planet by roughly 1 degree Celsius. That doesn't sound like much. It was enough to change the world. In Europe and North America, 1816 became known as the year without a summer. Snow fell in New England in June. Lakes froze in Pennsylvania in July. Crops failed across Britain, France, Switzerland, and the German states. Food prices doubled, then tripled. Bread riots broke out across the continent, the worst civil unrest Europe had seen since the French Revolution. In a rented villa on the shores of Lake Geneva, a young woman named Mary Shelley spent the summer trapped indoors by the unrelenting cold and rain. To pass the time, she and her companions agreed to write ghost stories. The story Mary Shelley wrote that summer became Frankenstein. The English painter J.M.W. Turner spent the same months capturing the strange yellow skies that the volcanic aerosols had produced. Skies whose orange hues he could not explain, but which we now know were Tambora's signature, refracted through the upper atmosphere. The historian John Post called what followed in Europe the last great subsistence crisis of the Western world. That is the story of Tambora that has been told many times. The story we are telling tonight has not. Because the most consequential effect of Tambora's eruption was not in Europe. It was in the Bay of Bengal. The summer monsoon is the largest weather system on Earth. It is driven by a single, simple physical contrast. When the Asian landmass heats up faster than the Indian Ocean, moist air rushes inland, and the seasonal rains arrive on schedule. Tambora's aerosol veil broke that contrast. The land could not heat the way it normally did. The temperature gradient flattened, and the monsoon faltered. A 2019 review in Wiley Interdisciplinary Review's Climate Change, led by climate scientist Christoph Reibler at the University of Bern, confirmed in detail what climate models had shown for years. A Tambora-scale eruption weakens the Asian summer monsoon, and it can do so for 2 consecutive years. In 1816, the monsoon failed. In 1817, it returned late and violently. The Ganges Delta, already one of the most biologically active waterways on Earth, went through a year of drought, followed by a year of unseasonal flooding. That sequence, drought, then flood, is the part that matters, because it didn't just hurt the harvest, it rewrote the chemistry of the bay. Vibrio cholera is a bacterium with an unusually adaptive genome. It lives naturally in brackish coastal water. Its virulence, its ability to make humans sick, is sensitive to 2 things: the salinity of the water it sits in and the temperature of that water. Change one, and you change the bacterium. Cholera was not new to Bengal. It had been endemic to the region for centuries, possibly for thousands of years. Local Bengalis worshipped a goddess named Ola Bibi, sometimes called the Lady of the Flux, to protect them from it. European doctors writing from the Indian subcontinent described a similar disease as far back as the early 1500s. But what existed before 1817 was a sporadic regional illness. Outbreaks would flare in one district, kill some hundreds or thousands, and recede. What emerged from the Bay of Bengal in 1817 was something fundamentally different. In his 2014 book, Tambora, The Eruption That Changed the World, published by Princeton University Press, University of Illinois professor Gillen Darcy Wood lays out the chain of causation in detail. He writes, quote, "The bizarre weather of 1816 to 1817, first drought, then late unseasonal flooding, altered the microbial ecology of the Bay of Bengal. The cholera bacterium, which has an unusually adaptive genetic structure, highly sensitive to changes in its aquatic environment, mutated into a new strain." End quote. That hypothesis was tested directly in a 2019 paper published in the journal Climate Research titled "Volcanic Mega Eruptions May Trigger Major Cholera Outbreaks." The authors examined 8 major volcanic eruptions over the past 500 years. Every single one was followed, within 2 years, by a major cholera outbreak in Bengal. Every single one. The mechanism the authors describe is a cascade. Eruption, then a disrupted El Niño cycle, then altered Bay of Bengal salinity and temperature, then an ecological window in which Vibrio cholerae could bloom and evolve into a more dangerous form. Tambora was the largest of those eruptions in the modern record, and the cholera outbreak that followed it was, by any measure available to historians, the largest in human history up to that point. In August of 1817, the new strain emerged in Jessore. By September, it was in Calcutta. By the following year, it was in Bombay, on the opposite side of the subcontinent. It moved with British military columns. It moved with merchant ships. It moved with Hindu pilgrims returning from the Kumbh Mela on the upper Ganges. According to records compiled by the Bengal Medical Board and later analyzed by historian David Arnold of the University of Warwick, the disease moved at roughly 60 miles per month, faster than any pandemic Europe had ever recorded. According to Encyclopedia Britannica, by 1820, the disease had reached Thailand, Indonesia, and the Philippines. On the island of Java alone, in the same Indonesian archipelago where the eruption had occurred 5 years earlier, more than 100,000 people died. In 1821, in the Iraqi port city of Basra, 18,000 people died in a 3-week period. The pandemic spread through Persia, into Ottoman Turkey, along the Mediterranean coast of Africa, and to the threshold of Europe itself, before a brutal winter in 1823 finally broke its momentum. Among the people who walked into the wreckage of that pandemic was an English clergyman named Reginald Heber. In 1823, the Church of England appointed him the second Bishop of Calcutta. His diocese covered all of British India, the island of Ceylon, parts of southern Africa, and Australia. It was, by area, the largest Anglican diocese in the world. He arrived in October of 1823. The pandemic had already been killing for 6 years. Heber's published journals, collected by his widow Amelia after his death and republished by Cambridge University Press, describe a country that has been hollowed out. He writes of villages where the houses are intact, but no one answers when he calls. Of fields that have not been planted because there is no one left to plant them. Of Hindu funeral pyres burning along the riverbanks day and night. He had come to India expecting to convert souls. What he found was a country burying them. Heber spent his short episcopate trying to understand what he was seeing. He could not. The medical theory of his time, the official position of the East India Company's sanitary commissioners, was that cholera was caused by what they called miasma, bad air rising from putrid swamps in unhygienic native quarters. The implicit blame fell on Indian customs, Indian poverty, Indian religious practice. Heber, to his credit, did not write that way. He wrote, instead, of his own helplessness, of his confusion, of his inability to comprehend why a loving God would permit suffering on such a scale. In April of 1826, in a small town in southern India called Trichinopoly, after performing a confirmation service in the oppressive afternoon heat, Reginald Heber retired to his quarters and stepped into a cold bath. He was found dead in the water minutes later. The cause? Recorded as apoplexy. He was 42 years old. He had been in the country for 2.5 years. He died believing the suffering he had witnessed was a mystery known only to God. It was not. The cause was physical, it was measurable, it was traceable, and it was sitting in the upper atmosphere above his head, and in the chemistry of the bay water beneath his ship, and in the genome of the organism that had been killing his parishioners. The science to see it would not arrive for almost 200 years. The total death toll of that first pandemic is genuinely unknowable. The colonial record-keeping was incomplete. Deaths in rural India, in Persia, in East Africa, were never systematically counted. But the scholarship is consistent on the order of magnitude. According to the World Health Organization and a body of 19th century historical research, cholera deaths in India alone between 1817 and 1860, across the first 3 pandemics, exceeded 15 million people. By the end of the 19th century, the global death toll from this lineage of cholera, originating in Bengal in 1817, ran into the tens of millions. It was, in the words of Professor Wood, the disease that, quote, shaped the 19th century like no other calamity. The chain of causation that connects Tambora to that death toll did not begin to assemble until almost 2 centuries later. It required ice cores drilled from the Greenland and Antarctic ice sheets, in which the sulfate signature of the 1815 eruption is still preserved as a distinct chemical band. It required tree ring data from teak forests in Myanmar and Vietnam, which recorded the growing seasons disrupted by the failed monsoons. It required coral records from the Indian Ocean. It required the genomic sequencing of Vibrio cholerae, a technology that did not exist until the late 20th century. And it required historians working with East India Company medical archives to map the disease's spread in space and time. Only when all of those datasets were laid against each other did the chain become visible. A mountain, a stratosphere, a bay, a bacterium, a pandemic that killed for 7 years and shaped a century. The first pandemic ended in 1824. 6 more would follow. In 1854, during the third pandemic, a London physician named John Snow traced an outbreak in the Soho district of London to a single contaminated water pump on Broad Street. His investigation is generally credited as the founding moment of modern epidemiology, the science of how diseases spread through populations. Almost everything in modern public health traces some part of its origin back to the long shadow of 1817. The international sanitary conferences of the 19th century, the predecessors of the World Health Organization, were convened specifically to coordinate cholera response. Modern urban water sanitation, sewage infrastructure, quarantine protocols, and intergovernmental health treaties all grew out of the European response to a disease that arrived from Bengal. The seventh cholera pandemic, by the way, is still ongoing. It began in 1961 in Indonesia, the same Indonesian archipelago that produced Tambora. According to the World Health Organization, it currently causes between 3 and 5 million infections worldwide every year.
Here is why this matters now. In December of 2024, CNN published an interview with Markus Stoffel, a climate professor at the University of Geneva. Stoffel and his colleagues estimate the probability of another Tambora-scale eruption in the current century at roughly 1 in 6. A 2017 study published in Nature Communications, led by climate scientist John Fasullo at the National Center for Atmospheric Research, found that because of changes in ocean stratification driven by modern global warming, a future Tambora-scale eruption would produce a stronger surface cooling response than the original one did. The year without a summer would be worse the next time. A risk modeling report from Lloyd's of London, also cited in that December 2024 CNN coverage, estimated that economic losses from a Tambora-equivalent eruption today could exceed $3.6 trillion in the first year alone. And the disease vectors, the Vibrio cholera in the Bay of Bengal, the influenza reservoirs in East Asia, the dengue and yellow fever mosquitoes that thrive in disrupted weather, they are still there, still adaptive, still waiting for the right window of temperature and salinity and human displacement to do what they did in 1817. In April of 1815, a mountain on a small island in Indonesia ended one summer. It started the pandemic that lasted 7 years and killed tens of millions. And the only reason we know that, the only reason we can connect those two events at all, is that the science to do it did not exist until about a decade ago. The question scientists are asking now is not whether it will happen again. The question is what we will fail to connect the next time it does.